Let's take a look at how we can draw common electric field patterns. Now, we've talked a little bit about electric fields. We've mentioned that they're force fields and that force will act on charges. We've also mentioned that we can use test charges to help us evaluate what the electric field would be at different positions. And we've even talked a little bit about a uniform electric field, and we actually did field line diagrams for that, and the field line diagrams were these straight, equally spaced lines with arrows on them. Let's take the very simplest case. We're just going to have a single charge. We'll make it a negative charge. So here's our single negative charge. First of all, this here, this one, that would be a vector field line representation. And all that you're doing there is you're imagining bringing in the test charge. Let's say I put the test charge right here. If that's the case, there would be, it's a positive test charge. It would be pulled towards that negative charge in the center with a certain force, and the force per unit charge would be the size of the electric field. And of course, we can represent that as a vector because electric field is a vector. And so wherever we place our positive test charge, there would be an electric field vector there. Of course, the closer you are to that charge, the bigger the vector will be. Now, we don't usually use the vector representation, and the reason is that these vectors start crossing each other and our diagrams will become hopelessly confusing. So we don't generally use these vector diagrams. And what we prefer to use is a field line diagram. Field line diagram doesn't give us quite as much detail, but it gives us a nice overall picture of what's going on with the field. And as I told you before, the field line diagrams, it shows you how strong the field is by how close the lines are together. So the stronger the field, the greater the line density. So from this diagram right here, I can tell that I've got a fairly weak field when I go out farther, and a fairly strong field when I'm in close, because there's a big gap between the lines out here, and just a little gap between the lines in close. The other thing that we need to know about the electric field, and we'd like to know it at every position if possible, is what direction will the electric field be in? And that's just simply shown with the arrows. Arrows show direction of field. And it's always going to be the same direction as the force on a positive charge. Now let's say we've got 2-point charges, and let's make one of them positive and one of them negative. So let's go with a positive charge over here and a negative charge over here. Now, of course, a positive charge would push positive charges away from it, so all the electric field lines would go away from the charge. Whereas on the other side, all of the electric field lines would point towards a negative charge because a positive charge would be attracted to the negative. Now, if we're to pick out a point, let's say we pick out a point right about here. Okay, so we would have a repulsive force from this positive charge which would push in this direction. Something like that. So that's supposed to be a vector representation of the field at that point. Now, the negative charge here, it's going to attract, so it's going to have, it's a little bit farther away, so it's going to produce a force that's a little bit less, so I'll draw my vector a little shorter, maybe something like that. And then if I was to add those two electric fields as vectors, I could use my parallelogram rule, and I should get something about like that. That would be my resultant electric field at that particular point. And what I could do is continue to evaluate the electric field at all different points. And what I would find is I'd get a pattern that looks something like this. If I pick out a point right here, I'd get a strong attractive force to this charge and a fairly weak repulsive force from this charge. I'd complete my parallelogram rule, and what would happen is I would get a resultant electric field vector that's tangential. It would be tangential to the electric field lines. So this field line representation, I can pick out any point on there and at least estimate what the direction of the field is going to be by the surrounding arrows. And I can get a decent sense of how strong the field is. Where does it get weaker? Well, you can see it's getting weak out here because there's a large spacing of the lines. Here's some metallic filings that have been placed around two charges. They must be let's say a positive charge and a negative charge. And you can see that there are naturally occurring lines here, and they're actually darkest right close to the charges themselves. In fact, if I were to draw the representation, it would look like that. If I consider this one over here on the right to be the positive charge, and this one over here on the left to be the negative charge. And then we can talk about the electric field at any individual point, such as these. The direction of the electric field will always be tangential to the field lines. If we have like charges, but we get a repulsive pattern that would look something like the following. There'll be a few errors in this, but it won't be too bad. You can see that in the repulsive pattern, you don't see any field lines right in the center here. There would be 0 electric field equals 0 right in the center of that pattern. And let's make them both, say, positive charges, and then we can put the arrows on. It would always go away from the charges, like so. And we're seeing the strongest field in close to the charges. We're getting the strongest field. Notice that the field lines never touch each other. If the field lines were to touch each other, what that would be saying is that the line density is infinite. If the line density is infinite, that would mean your electric field would be infinite. So the field lines can never touch each other, because that would mean infinite field, since infinite line density. And of course, if they never touch, they can never cross as well. It wouldn't make sense if the field lines cross, because if they crossed, you'd be saying, I don't know what direction the electric field is in, because it would look something like so, right? So if the two lines cross, what direction would you say the field is right here? Is it in this direction along that field line, or is it in this direction along that field line? So two directions is, well, it's a lot of nonsense. That's not possible. We can't have two directions to the electric field at once. And we talked about there being a uniform field inside parallel plates. So this is a basic situation where we have two plates, and we'd have some sort of battery that we would connect across here. I'll make the top plate positive, and there would be positive charges that would accumulate on the top plate, and negative charges would accumulate along the bottom plate. And in that situation, with the parallel plates, we'd get a uniform field, and you'd draw the pattern about like that. So we're getting, you should see equal spacing between those field lines, always the same. And they're always parallel. So all these lines are parallel. They're pointing from the positive plate to the negative plate. Now you do get some end effects. So if you're out here, the field is no longer uniform as you go beyond the edges. So that's an edge effect. Here's an interesting situation. We've got just a plate across here. Let's make the plate say positive, and we can make our conducting circle over here. We can make it say negative, and you can see the field lines are doing something about like that, and they would go from the positive to the negative. I've tried to draw all the field lines so that they come into the conductor at a perpendicular angle, and they come out here as well at a perpendicular angle. So these should all be perpendicular. And the reason for that is if we have any part of the electric field that's along the surface, that electric field will cause the electrons to move along the surface, and we'll get surface currents. Well, we know we don't get surface currents. So all the electric field has to be directed perpendicular to the surface of the conductor. In that direction, the metallic bonding can hold the electrons, so you don't get any current. The electrons don't leave the conductor. Another thing that's very interesting about this, if you notice inside here, there's no field lines. There's no electric field at all. There's no electric field inside a conductor. That's very important. What happens is that the charge goes to the outside of the conductor in such a way that it cancels out all the electric field inside the conductor. What I've drawn in here isn't a solid conductor, but it could be, and it's probably a better case where we do have a solid conductor. So we're getting no electric field at all inside the conductor. And that makes sense because remember, in a metal, we've got all these free electrons. Now, if there is any sort of electric field inside the conductor, the electrons will move and we'll get a current. There might be a transitional current when you first switch the battery on, you create the positive and negative charge on the two conductors here. There might be a transitional current, but we know it dies down very, very quickly. And if there's no currents inside the conductor, then there can be no electric field inside the conductor. So the electrons just arrange themselves. They get as far away from each other as possible. The charge gets as far away from each other as possible. And it arranges itself in such a way that there's no electric field inside the conductor. This idea that there's no electric field in a conductor leads to the idea of electric shielding, which is very, very important. So for instance, if I imagine this rectangle here, this rectangular conductor, the charges go to the outside surface. They tend to accumulate in the corners. So if I pick out any point in here, then okay, there's a bunch of charges in the corner here that are pushing away in that direction. But there's some here that are kind of pushing back in about that direction. And some here that are pushing back in about that direction. And then there's some back here that are pushing back in that direction. And if I add up those four forces, those four electric fields, I get zero. I get zero force, zero electric field acting on all the electrons, all the free electrons inside. And so we still have zero electric field in here. And even if you've got all kinds of electric fields out here, and of course there's all kinds of electric fields all around us all the time, especially electromagnetic fields, then the charges out here on the outside, what they're going to do, all these charges on the outside, they're going to move around as they're exposed to these electric and magnetic fields. And they'll move around in such a way that they'll always keep the electric field inside zero. So they effectively shield the inside of the conductor. And that has some really important effects. This guy here, he's perfectly safe because the electric field inside of this fence that he's in is zero. He's basically inside of a conductor. And even though there's holes in that conductor, it'll still shield out the electric field. You've probably looked at cable wires. There's always this copper mesh around some insulation, and then you've got the signal wire. This is the signal wire here coming out. But you need the copper wire on the outside, and that's for shielding, so that the signal wire isn't going to be interfered with by all the external signals, all the external electromagnetic waves. And this last one here, we've got a car being hit effectively by lightning, but inside the car, E is zero. So you should still be safe inside your car. It's basically a metal box. You should still be safe inside your car when it is hit by lightning. Here's a little IB question. Stop the video now, read over the question, and see if you can work out the answer. Okay, so hopefully what you said was the correct answer is this one here. It's a charged spherical conductor. So it's a conductor. The electric field has to be zero on the inside. So there you've got the E equals zero. Once you get outside that conductor, then the electric field will drop off, basically as 1 over r squared. And just to summarize, we've got a few rules that we can use if we want to draw field line diagrams. First one is that, of course, the field lines point towards negative charges and away from positive charges because they're always in the same direction as the force on a positive charge. Secondly, field lines push off if the charges are like. If, for instance, we've got 2 positive charges, then the field lines will not touch, but they'll push off each other, something like that, etc. If the charges are opposite, of course, the field lines join up, so you get a pattern that looks more like a plus and a minus, opposite charges, and you get this type of pattern here. Next, there's going to be proportionally more field lines coming out of bigger charges. So if I've got a charge, say Q, and I've got a charge 2Q, if I put 4 lines coming out of Q, I should have 8 lines coming out of 2Q. So twice as much charge, twice as much electric field. If you've got a conductor, there will be no field lines inside a conductor. So that's the idea of shielding. If you've got a conductor, E equals 0 inside. That's not going to be true for an insulator, just for a conductor. And the other thing is that for a conductor, the field lines are going to emerge perpendicular to the surface. And if they don't emerge perpendicular to the surface, you'd get surface currents. So we'd have to have, say, electric field line coming out like that, perpendicular to the surface. They can curve afterwards, but they've got to come out perpendicular to the surface. So the metallic bonding will hold the electrons or hold the charges from escaping, but there's nothing to keep them from moving along the surface and creating currents. And we know we don't get currents, so the field lines have to emerge perpendicular. Okay, what we're going to try to do now is sketch a field line diagram for this situation here in which we've got a positive charge and 2 negative charges. What I'd like you to do is try this exercise on your own and then come back for the answer. So let's start with the joining pattern between positive and negatives. So I can have a joining pattern here between this positive and negative. So we're going to get something like that. Same thing over here with this positive and negative. And try to draw your field lines so that you do get them coming out perpendicular. I should have the field lines a little closer together. I should have the field lines a little closer together on this side of the charge than on the far side because the field lines are being pulled. And we'll do another joining pattern here between the positive and negative. I'm now up to 5 lines coming out of the positive charge. I'm just going to have one more line, maybe something like that. And that gives me 6 lines out of the positive charge. And then I want to have 6 lines going into each of the negative charges. We should have first of all start with that repulsive pattern between the 2 negatives. They're pushing off each other. So I'm now up to 4 lines. So I need to put 2 more lines in there and 2 more lines, 3 more lines in fact, in there. And all of these lines would be going, heading in towards the negative charge. Now there would be a point somewhere in here where we'd get 0 electric field. Of course we can't represent line density of 0, but we would get 0 electric field in there somewhere. And so the fields are kind of canceling out in that region. And that's why you get large spacing in that region here. Now what I'd like to do is look at a particular point, this particular point right here. And what I'm going to do is add up the 3 electric field vectors and see if the resulting electric field is tangential to the curve at that point. Let's see if I've approximately at least done a good job with my field line representation. So this positive charge right here, it's going to push a positive test charge away. It's quite close, so that'll be a fairly strong force. I'll call that my first electric field. I'll get another force, not quite as big because this negative charge is a little farther away, pointing directly towards that negative charge there, and I'll call that my second electric field. And then the other one, it's going to be a very small electric field contribution due to that charge in the upper right, and I'll call that electric field number 1. Now if I add those three vectors, that means just join those together. And I've drawn them roughly to scale. And let's see what it looks like. So I'm going to start with my vector 1. I'm just going to try to redraw it there. There's my vector 1. I'm going to add that to vector 2. Just try to reproduce vector 2 there, join them head to tail, and then I add that to vector 3, which is just a short one coming up, something like that, so that my resultant would be that. That's my resultant electric field at that point. So if I come back here and reproduce that line, you can see that to a good approximation, it seems to be tangential to my electric field line. I've done not too bad of a job of drawing my electric field pattern. And that's all for today, folks. Thank you very much.